Welcome to Math with Malia. Today we're going to be covering Eureka Squared, Math 7 and 8, Module 6, Lesson 4, Multi-Stage Experiments. In the previous lessons we learned about what probability is, what empirical probability is, or experimental probability, the actual data results of our experiment, and then we learned about theoretical probability, what we would expect to happen from a chance experiment. Today we're going to talk about experiments that have different stages, okay, and how to calculate theoretical probabilities using a tree diagram to keep all of our data and our outcomes organized. So let's first just review what a sample space is. A sample space for a chance experiment is what the possible outcomes could be. So for example, number 1, rolling a 6-sided number cube with the numbers 1 through 6 on its faces. Well, the possible outcomes we could roll would be getting the number 1, the number 2, the number 3, 4, 5, or 6. So that is the sample space. For number 2, our chance experiment is selecting a marble from a bag containing 3 marbles. So as we do the experiment, we have a chance of pulling either marble 1 or pulling marble 2 or pulling marble 3. That is our sample space. Those are the possible results. We're not looking at actual numbers for the probabilities, just what are the possible results we could get. For number 3, selecting a cube from a bag containing 4 blue cubes and 1 yellow cube, well, we have a total of 5 cubes in our bag. So our sample space, or the possible results we could get, would be pulling cube number 1, pulling cube number 2, or cube 3, or cube 4, or cube 5. Whatever colors those cubes are would help us then determine probability. But the sample size is just each individual cube that could be pulled. And for our last chance experiment, flipping a fair coin, meaning it's not weighted more heavily on either side. And the results we could either get heads or tails. So knowing about sample space will help us as we're building our tree diagrams. Okay, so we can see that in that video, our chance experiment had 3 different stages. Stage 1, we would choose the bread, and it was random. She spun the spinner and would randomly pick her bread. Then we had stage 2, which was randomly choosing the protein, either chicken, tofu, or egg salad. And the last stage, the 3rd stage, was randomly choosing the vegetable, spinach, lettuce, or kale. So we had 3 different stages, and each stage had 3 equally likely outcomes. So the bread stage, the first stage, had 3 equally likely outcomes. We could get either the wheat, the bagel, or the pita bread. And stage 2 also had 3 equally likely outcomes. We could choose the chicken, the tofu, or the egg salad. Stage 3, same thing, we had 3 equally likely outcomes. We could get either the spinach, the lettuce, or the kale. So let's make a list of as many possible unique sandwiches we can think of for this chance experiment. we could get wheat, and then chicken, and then spinach. Okay. We could get a bagel. I'm just going to go kind of all the second choices now. Bagel, tofu, and lettuce. Now I'm going to do the third choices. I could get pita, egg salad, and kale. I could get wheat, and I'm just going to change one choice. Instead of chicken, I could get tofu, and then keep spinach. I could get a bagel, and I'm going to just choose a different middle protein option. So instead of tofu, let's choose egg salad, and I'm still going to choose lettuce. So we could keep doing this and try to list all of the possible outcomes. But are we going to get every single one? Could we possibly repeat or duplicate an outcome? Could we possibly miss one of the possible outcomes? So using a tree diagram will help us to organize and accurately record all of the possible outcomes so we don't miss anything or we don't duplicate any results. So how do we create a tree diagram? Well, a tree diagram is a graphical representation that displays all possible sequences of outcomes in a multi-stage experiment. The tree starts by displaying 2 or more branches that represent the possible outcomes in the first stage, and then each stage then continues to have branches to represent the possible outcomes for each stage. So you can think of each dot in the tree diagram representing a stage. So our first stage was choosing the bread. What are the choices for bread? Well, we had 3 possible choices. Okay, so our first stage was choosing the bread, and we could choose either wheat bread, or we could choose a bagel, or we could choose pita bread. That's the first stage. The second stage, I'm going to have new dots for the second stage, and each second stage had 3 choices for protein. I would have 3 choices for protein. Okay, so I'm going to show you how the completed tree diagram would look. It's important to note that each dot on the tree diagram represents a phase. And it's a good idea to try to keep your phase dots organized so they're stacked vertically with each other. That way you can see each stage all branched out. And it's important to label each branch as you go. So our second stage choices, we're choosing the protein. We could have chicken or tofu or egg salad. Okay, and so then we would label each branch. Okay, and then the next stage, I'm just going to show you briefly, would have dots for the next stage, and then each stage 3 had 3 choices or 3 possible outcomes. So here's what the completed tree diagram would look like. Again, you can see here is stage 1 represented by the first dot. Okay, this is stage 1 where we are choosing our bread. And we could choose bagel, wheat, or pita. Stage 2, you can see these dots for stage 2 are stacked vertically on each other. And this represents choosing the protein options. We could choose tofu, chicken, or egg salad. And then you can see that the next phase or the next stage of the chance experiment is represented by these dots. They're again stacked vertically, so it's nice and organized. This is where we are choosing our vegetable options. And again, 3 different possible outcomes for the vegetable: kale, spinach, or lettuce. So what do you think these final dots represent on the ends of our tree diagram? Well, these are the possible unique sandwiches of this chance experiment. Each of these individual dots at the end of our tree diagram represent the possible unique outcomes. Okay, so the total outcomes and the sequence we get there. We could choose a bagel, tofu, kale. We could choose a bagel, chicken, kale. So all the possible combinations are represented by these dots at the end of our tree diagram. So now that our tree diagram is completed and all of the details and the possible outcomes are labeled, we can use that tree diagram to answer questions about probability. Using the tree diagram, determine the number of unique sandwiches that can be made. So if we're looking at our tree diagram, again, the dots on the outside or the ends of our tree diagram represent the total possible unique outcomes. We can see that we have 27 total possible outcomes at the end of our tree diagram. So that represents 27 unique sandwiches. Do you recognize the relationship between that? I have 3 stages, and each stage had 3 different outcomes. So stage 1 had 3 possible outcomes. Stage 2 had 3 possible outcomes. Stage 3 had 3 possible outcomes. What is 3 cubed, or 3 to the 3rd power? It equals 27. Okay, number 4. Imagine that your partner chooses a unique sandwich. If you choose each ingredient at random, what is the theoretical probability that you make your partner's sandwich? What is the theoretical or expected probability that you will pick the exact same sandwich that your partner did? Well, how many unique sandwiches are there? 27. If your partner chooses one out of the 27, the chance of you picking the exact same would be only 1 out of 27. There's only one chance that you would pick the same exact thing because there are no duplicate sandwiches. How do we see this theoretical probability in the diagram? Well, this is just represented by the dots at the end of our tree diagram. Each dot or endpoint of our tree diagram represents one possible outcome. So we could just say that the ends of the tree diagram represent one possible outcome. If you pick each ingredient at random, what is the theoretical probability that you make a chicken sandwich? Okay, so again, we're looking for the expected probability. What's the expected ratio out of the total? So we know we have a total of 27 possibilities. How many of those possible outcomes are chicken sandwiches? So if we look back at our tree diagram, this is why it's important to have a really nice organized tree diagram with all of the outcomes labeled so we can easily answer the probability questions. So I'm looking for chicken sandwiches. So from here, I have chicken, and I can have chicken kale, chicken spinach, or chicken lettuce. If I chose wheat, I have chicken, and I could have kale, spinach, or lettuce. If I choose pita, I would have chicken, and then I would have kale, spinach, or lettuce. So I have 9 total possible outcomes with a chicken sandwich. It doesn't matter what the other outcomes are as long as my protein is chicken. So we have a total of 9 out of 27 possibilities of having a chicken sandwich. And if we simplify that probability, we would get 1/3, or about a 33% chance of getting a chicken sandwich. Okay, number 6. Here's our next chance experiment. It's multi-stage. We're playing spinners and dice. The player spins each spinner once and then rolls a fair 6-sided dice. The score is the sum of each spinner and the number that the die lands on. So spinning the first spinner, this would be stage 1 of our experiment. Then stage 2 would be represented by spinning the second spinner. And stage 3 is representing rolling the die. So we're going to make a tree diagram of each outcome or each possible sum that we could have from this multi-stage chance experiment. So again, remember, 1 dot represents each stage. So our first dot would represent stage 1. How many possible outcomes or branches would we have from our first dot? Well, I'm just going to start it here. Here's our first dot for stage 1. We have 2 possibilities. We could get 1 or we could spin a 3. Then stage 2 would get their own dots, and each dot at stage 2 has 2 possibilities. Okay, we could roll a 1 and a 6, 1 or a 6. This is where it's going to get complicated, and make sure we want to keep it nice and organized. At stage 3, Each dot has how many possible outcomes? Well, we would have 6 possible outcomes at each dot. Each dot at stage 3 has 6 possible outcomes, so you would want to make sure to label each outcome, and then at the end we want to label the sequence to get to the sum. So for instance, here, if we spun a 1, and then we spun a 1 again, and then rolled a 1, our sequence would be 1, then 1, then 1, and our sum would be 3. So we want to make sure we label the outcomes at the end of our tree diagram. So here's what the tree diagram would look like for this chance experiment with the spinners and die. Again, here's stage 1, where we rolled the first spinner. Stage 2 is represented here, where we rolled the second spinner. And then stage 3 is represented here by the third section of dots, and we can see that each dot at stage 3 has 6 possible outcomes. And then we've labeled the sequence and the sum for each possible outcome. So how many possible outcomes do we have? Well, we have 6 plus 6 plus 6 plus 6. We have 24 possible outcomes. They're all unique. What is the theoretical probability of scoring exactly 8? So again, out of our total of 24 possible outcomes, how many score exactly 8? If we look back at our tree diagram, since it's already organized and labeled, we can just find the outcomes that have a score of exactly 8. So exactly 8, our sum of exactly 8. So only 3 out of the total 24 would give us a sum of exactly 8. Okay, since we were looking for exactly 8. And if we simplified that ratio, we would get 1 out of 8 chance to get exactly 8. Part C, what is the theoretical probability of scoring at least 10? So our sum needs to be at least 10. So let's go back to our tree diagram, and we're going to circle or highlight the numbers that are at least 10. At least 10. 10. That's at least 10. 10 or higher. So we can see we could not get a sum of at least 10 if we rolled or we spun a 1 and a 1 on both spinners. That would not get us there. No possible options if we started with 1 on the spinners. We had to start with a 1 and then at least get a 6. So how many total outcomes gave us a sum of at least 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 out of a total of 24 gave us a score of at least 10. So using tree diagrams is a great way to organize and represent the possible outcomes of a multi-stage experiment. It's important to make sure it's organized and labeled clearly so that you can answer probability questions easily afterward. Okay, so once we've recorded all the details, we can calculate theoretical probabilities by looking at the outcomes and the sequence of how to get each unique outcome. Make sure to leave any comments or questions you have, and we'll be back here for lesson 5.